Still not opening. Okay. I think it's finally gotten there. Now, we are recording. Any questions before we get started on today? Okay. If not, we were on page 63, step and piecewise defined functions, and we talked about the greatest integer function, which we already discussed. This was the last slide on that, and we were getting ready to talk about the characteristics of the step and piecewise defined functions. So as soon as I can get, there we go. Everything is really, really slow. I guess since you didn't shut down the computer, all the little electrons got tired having to run all night, so they're slow today. Okay, well, thought it was, there we go. Slow, but here. All right, now remember our step or piecewise defined functions. Step functions go like steps. They can be going downhill, up here, it doesn't matter. And we're mostly talking about step functions on this. So even though it says and piecewise defined functions, they are a type of piecewise defined function, but all of these characteristics apply to step functions, not necessarily other piecewise defined functions. What is the domain of, generally, of all real numbers? Yeah. How about the range? Say again? Okay. Think about the graphs of these. Let's see, was that on the previous one? Yeah. Here's the graph. So, yes, the integers only. Okay? Because if you shine the light from way over here, way over there, then you would only have the integers darkened here, because the things in between, there are no values for those. So it's all integers, positive and negative integers. So the range is a set of all integers. How about x-intercept? Yes, well, that's the y-intercept for sure. The x-intercept is everything in between 0 and 1. And again, you see it here. The y-intercept is that point right there. Not there, because that's an open circle. Just at 1, 0, 0. The x-intercepts are everything between 0, 0, and 1, counting 0, 0, but not counting 1, 0. Okay? So that would be a parentheses there. So that's why the x-intercepts are an interval. The y-intercept, of course, is a point. The y-intercept will never be an interval. Why? Because Ryan came in. That's why. Now, why will the y-intercept never be an interval rather than a single point? Okay. What's that? Okay, for this one, yeah, that's the reason there. But why will, for any function, you'll never have a range as of an interval, of a y-intercept, or anywhere else. Okay, well, you're close, and you may have said, I couldn't understand all you said, but if you had y-intercepts in a range, then vertical line test fails miserably there, because you have more than one y value for a given x value. Couldn't happen anywhere. You couldn't have a range of y's anywhere, because any vertical line that included that range would have multiple points. And remember, the definition of function for any given x is 1 and only one y. So that would knock that out. Okay. The graph is constant between each pair of consecutive integers of x, interval values of x, and typically it increases in steps. So we don't call it an increasing function. It's not a constant function. It's constant between each pair of consecutive integers. That's about all you can say. The graph jumps vertically. This is the second part of that. 1 unit at each interval value. So, I'm sorry. In a small sense, it's kind of like an increasing function with lots of constants in between. So we don't say it's an increasing function, and we say it's constant in this, but it does going upward. Now, if you put a minus sign in front of that, it would be going downhill. So, and still constant intervals there. So, those are the characteristics. They're rather strange compared to our other ones. They do have a little hint here that quite often I forget to notice and say. If you're using a graphing utility, read that to mean a graphing calculator or something like that, okay? If you're using a graphing utility to graph a step function or any piecewise defined function, you should set your graphing utility to dot mode, okay? There's two modes for graphing. One is, what do they call it? Continuous mode or something like that, and the other is dot mode. If you do continuous, then it's going to draw a line between every step. So you think there are vertical lines in there. There are not, okay? In fact, it won't be quite vertical because the computer won't do that. So it'll have from that last thing here to there, but it looks basically vertical. So basically, if you get in dot mode, it'll just fill in all the dots here, and then jump up here, fill in all the dots, and jump up here. You'll sometimes see some spaces between those, but you get a lot better idea what the graph looks like. Okay. Otherwise, it really does look like a set of steps. Okay. So now let's move to example 2. Evaluate the function at these 3 values. So let's do it. How do we evaluate? Well, let me get my pen activated. If it'll come up. Here we go. I think I'm going to have to use the dark blue. What we're looking for is f of negative 1, where your f of x is greatest integer in x plus 1. So how do we proceed? We're doing x equal negative 1. What would you write down first? Okay. Greatest integer is negative 1. Okay. Plus 1. And what is the greatest integer in negative 1? Remember the definition? The greatest integer, the integer greater than or equal to what's inside there. Not 1. This is absolute value. It is negative 1. So that would be negative 1 plus 1, and that would be 0. Okay? Let's do 2. F of 2. What would that be? The greatest integer in 2 plus 1. What's the greatest integer in 2? 2. Okay, we got that one down. Plus 1 is 3. All right, got it. How about this one? F of 3 halves. What's the greatest integer in 3 halves? Plus 1. Okay, greatest integer in 3 halves is 1. The greatest integer less than or equal to 3 halves, that's 1, plus 1, that's 2. Okay. Want to just see what that one looks like on a graph here. We already did minus 1, 0. So right there is a point, we know. Plus 2, 3. There's 1, 2, 1, 2, 3. So that would be this point is on it. Okay. And 1 half, 2, or 3 halves, 1. 3 halves is in between that, and that would be 1. That would be on it. So this would be like this. Oops, wrong answer. I put. Oh, 2. Yeah, I'm sorry, that's 2. I thought that's. I looked at it and wrote it in the wrong place. Okay. Knock that one out. Okay. All right. The pen didn't come back when it was supposed to. Okay, there was my origin right here, wasn't it? Okay. Okay, so we had this, open circle here, we had this with an open circle there, that with an open circle there, and so on. If you went back here, that with an open circle here. And it looks a lot like what we had before. What's the one difference? Let's jump back one page, 2 pages. This one started at 0 and moved to the right. This one starts at -1 and goes to the right. Actually, that's not exactly what happened. That's what it looks like. By the way, I think I forgot to mark you when you came in. Ashland, right? No, I'm sorry. Huh? Ann, sorry. It was one of those A words with Anna, right? Okay, good deal. Okay. Actually, what you did, and we'll talk about this in the next section, what you did is not shift everything to the left. What you did was shifted everything up. Because, look at this. It goes up here, this goes up here. And that's exactly what you see happening here. Everyone is shifted up. Why do we say that? Because you had the absolute value, the greatest energy function, and you added 1 to it, which is a vertical shift. We haven't done it yet, but no extra charge for hitting it early. Okay, so this is what the graph looks like. And if you see in your book, their picture is almost as pretty as mine. So, any questions? Let's clear that. You don't have to look in the book. You can watch right here. Let's clear all this ink. And greatest integer, x equal -1. Greatest integer less than or equal to -1 is -1. So that would be -1 plus 1 is 0. Okay? Greatest integer in 2 is 2 plus 1 is 3. The greatest integer in 3/2 is 1. Less than or equal to 3/2 is 1. So f of 3/2 would be greatest integer in 3/2 plus 1. That would be 1 plus 1. 2, didn't know you'd be doing such high-level math today, did you, when you came in? 1 plus 1 is 2. Okay, we got it. All right, here's the graph of it, and you see it's just like the one that was listed a couple slides ago, but everything has been shifted up 1. Okay, and that's exactly what's happened when you add 1 to the greatest energy function. Does that make sense? All right, good deal. When we use this, not very frequently, okay, but they love to do it because it is a piecewise defined function. All right, let's see. We now are going to graph another type of piecewise defined function. I think I'll graph it on this page here. And they don't have this on the slide, so I'll do it here. Sketch the graph of this piecewise defined function, f of x. And this is equal to, it's got 2 pieces. The first piece is 2x plus 3. And this is good anytime x is less than or equal to 1. And it's minus x plus 4. And that's anytime x is greater than 1. And it says to graph it. That's all it says, sketch the graph of it. So how do you like to graph functions? There are several ways. What would be the technique that you would suggest and propose that we do? Okay, you're going to use that. Okay, that fits both of these. These are both linear pieces, so you can certainly do that. So let's set up the graph. I think probably right here will be a decent enough place to put it. Okay, we'll put a few values in here. 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4, 5, 6, 7, 8. Up 1, 2, 3, 4, 5, 6, 7, 8. Down 1, 2, 3, 4, 6, 7. Okay, something like that. Okay, so mx plus b. What do you mean by that? What would be your next step? Say again? Okay, and do it. How would you do that? Okay, 0, 3, because that's the y-intercept here. 0, 3 would be right here. Now, I'm going to try to be sort of careful with this. What I'm going to do is start off just putting an open circle there. I'm not doing much of a good job of that. Not suggesting that's not an answer, but what I'm saying is let's just identify it for now. Okay, and then what would you do from there? Okay, because the slope is 2, then you do up 1, right 1. Okay, so it would be here, up 2, right 1, it would be here. Up 2, right 1 almost goes off scale. And you could also do down 2, left 1. That would be here. Down 2, left 1 would be here. Down 2, left 1 would be here. Down 2, left 1 would be there. Down 2, left 1 would be there. All right. Yes. Right. Okay. So that's what that line would look like. And what I'm going to do is connect the dots, but I'm going to do it with a dotted line. Now, there's a reason for that. Because this function is not defined everywhere that way. It's only defined where? Where it's less than or equal to 1. Well, where is x equal to 1? Write 1 and go up until you find the function, and it seems to be right there. And it's equal to it, so I'm going to fill in that dot and then complete my line down here. So all these points are on there, these are not. So I could erase those if I wanted to. I think I will, since I've got a magic pen that will do that easily. So those are not on the function. The endpoint 1 is because of that equal sign. Okay, what would you do with the next part? Okay, go up to 0, 4, right there. And again, I'm just going to put a little mark there. Down 1, right 1. Down 1, right 1. Somewhere there. Down 1, right 1. Down 1, right 1. Down 1, right 1. Somewhere. 1, 2, 3. I think I'm down to here. I wasn't coming down fast enough. This one should be here. This should be there, 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 there. Okay, something like that. Now, again, I'm going to sort of fill in the blank here, but this is only good where? Greater than 1, so it doesn't count at 1, so that one becomes an open circle, but greater than 1 will be anything to the right, okay? So that's what it looks like, and basically I can go back, probably a good idea, and erase these pieces here, but I erased too much. Okay. All right. Something like that. Okay. See how it works? The important thing here, now, not always will they give you linear functions, so they may not be quite this easy, but that's the deal. I would draw the graph even for this equal to 1. You see, we did that. We just make that an open circle. And then the function goes up to that. If this was a quadratic or a cubic or anything else, it does whatever wiggling around it does. When it comes to 1, that's an open circle, but it goes right up to that open circle. This one, where it's equal to, it includes that endpoint. And this could have been a cubic, a quadratic, a square root, or whatever other function you wanted it to be. Whatever it was, it would then be that shape up to and including that endpoint. But you see, what's the domain of this? All real numbers. Certainly all these values are hit by this line, all these values are hit by this line, but you have to make sure you have one and only one value for this one, the one up there, not the one here. But you need one for every point on the other side, so this line needs to go all the way to there, that one needs to go all the way to there. You see what I'm talking about? Don't say, well, it's greater than or greater than 1, so I'll start at 2. Well, yeah, you'll put a point there, but you got to backtrack and go all the way to where 1 would have been, but make that would have been a hole, and then go all the way to the hole. Does that make sense? Okay. Good deal on that. And if you look in the book, again, they tried to do a pretty picture, but not as good as ours. Okay. They do have a checkpoint here, as they do after every example. Please do the checkpoints just to make sure you understand how they work. All right, we talked about these functions now. We're going to give them a name, the parent functions, because from these functions, all other functions basically are derived. And here's what they are. The 8 graphs of the shown below represent the most commonly used functions in algebra. Okay? The constant function. It could be a positive value here. That looks like maybe 1.2. It could be a negative value. It could even be 0. It could be an irrational number, right? It doesn't matter. But remember what are some of the characteristics of that? Domain, all real numbers, range. Yeah, y is equal to c. That's the only value you have for the range. And whatever that constant is, okay? Y-intercept. 0c. Y-intercept is where x is 0 and the y is always c. So it's 0c. How about x-intercept? None on this one. The only time you have an x-intercept for a constant function is when it's f of x equals 0, and then every point on the x-axis is an intercept, and the y-intercept is 0, 0, that one and only. Okay, then the identity function. This is nice, pretty, again, a straight line. F of x is equal to x, but this time, what's the difference? Any difference? The y-intercept is not c, it's 0, 0, which now becomes the x-intercept as well, okay? How about its slope? 1, because the coefficient of x is 1, the b here is 0. That's why the y-intercept is 0, 0. Again, a straight line, and it goes from there. The next one that's sort of straight line-ish is absolute value function. Okay? How does it differ from the identity function? It's never negative. So where this one goes negative, this one has to go up and go positive. The opposite of that. And just as a hint, absolute value functions just about always produce a V shape. Okay? It may not be at the origin. This one is. The parent function is at the origin. That V can be translated elsewhere. It can actually be inverted and translated elsewhere as well. Okay? But absolute value functions typically have that V shape. Square root of x function, the square root function. What do you notice about it? Okay, it's only in the first quadrant, means that the domain does not include any negative numbers when you have that, because what's inside the radical cannot be negative. The range, because this is a principal square root, that's positive, so it's only positive, so it's only 0 to positive. Now, sort of wish they hadn't done this one first, but we'll see that looks a lot like the squaring function, only it's sleepy. It's lying on its side and only got half of it. Okay? So let's move on to the squaring function, or the quadratic function, and that's how it looks. Now notice, ever since the constant function, everyone has had an intercept at 0, 0. X-intercept and Y-intercept. These are the parent functions. Other functions will not always be this way, but the parent functions quite often do begin there. This one does, this one does. This one doesn't, and even that one does. Okay? Now, quadratic function, what do we call that shape? Parabola. And as I said before, the square root function is a sleeping parabola, only half of it, on its side, and that's what that looks like. Okay? Cubic function, again, goes through 0, 0. I guess we ought to say this. Increasing, decreasing here. How would you describe that? Decreasing from negative infinity to 0. And remember, you're talking about the x's there, not the y's. It happened to fit for the y's, but you're talking about the x's there, and it's increasing from 0 to positive infinity. How about that cubic function? Increasing everywhere over the entire domain, which is all real numbers. Okay? Good deal? Then the reciprocal function, 1 over x. What do you notice about it? Decreasing everywhere, absolutely right, except one place. Second? At the origin, is that what you said? Absolutely. X cannot equal 0. So it's not defined at the origin. It's not defined at x equals 0. So of course it can't be decreasing there. Okay? So it's decreasing everywhere it's defined, but its domain is from negative infinity to, how do we express that? Okay. Everywhere except x equals 0. That's, to me, the quickest way to do it. Do it in interval notation from negative infinity to 0, then put a parentheses by 0, union that with parentheses 0 again. That means you don't include the 0 everywhere positive after that. Because you can get as close to 0 as you want to, but you can't reach 0. So everywhere that it's defined is decreasing. It's just not defined as 0. And then the greatest integer function, which is one type of a step function, and we just gone over that, so nothing new. Any questions on those? Familiarity with the basic characteristics of these simple graphs will help you analyze the shapes of more complicated graphs, in particular graphs obtained when these graphs by rigid and non-rigid transformation. What are they talking about? That's the next section. But let me say this while we're here, especially when you have the cubic function here. This is the parent function. Once you start introducing more terms, like a square term, a linear term, constant term, or any combination of those, maybe leaving one or two of them out, doesn't matter. But what you do then, notice how it comes up and looks like it's trying to bend down. But then it continues on up, always increasing. Once you start adding those other terms, you'll find that you do get a relative maximum here. It dips down and then does a relative minimum and goes back up. So your cubic function looks the most different from this, from the others. The others all look pretty similar, but the cubic function, typically, if you have more terms there, you have two, typically have two. One lobe here, one there. You can change signs and have a lobe here or there, you know. It can do that, but to me, it's the one that looks most dissimilar to its reciprocal, to its parent function. Okay? Make sense? Okay. That is the last slide for this section. So let's look at vocabulary. In exercises 1 through 9, match each function with its name. So I'm going to go back to this slide here and clear the ink and write well, you got your books, most of you, right? The first one is f of x is, I still need to do it, because if I call it out, I'll give the answer away. This is the first function. What is the name of that one? The what? Okay. It's which specific step function? Say again? Greatest integer function. Which one's that? Nope. G, isn't it? Okay. Greatest integer function in my book is a G. In your book it's an H? Really? Huh? I know. Oh, no. Okay. We're doing these. Oh, vocabulary. Top of the next page. Sorry about that. Okay. Yeah. Got it. Okay. We're doing vocabulary, top of page at 65. Okay. Number 2. F of x is equal to x. That's what? Identity function. Which letter is that? I, got it, okay? Alpha of x equal 1 over x. What's that? The what? Reciprocal function, which is that? H, very good. Number 4, alpha of x equal, okay, that's A, the squaring function. I was afraid if I read it out, I'd give it away. Okay, the next one is alpha of x is equal to, and which is that? B, excellent. The next one, alpha of x equals C. Constant function, which is that? E, excellent. The next one, alpha of x is equal to an x with 2 bars around it, one on either side. Absolute value function, which is F, very good. 8 is alpha of x equal x raised to the 3rd power. Cubic function, that's C. And there they threw one in that wasn't a parent function, but it's okay. Alpha of x equal ax plus b. It's what? Linear function. Which others of these that we named were also linear functions? The identity function was a linear function, and the constant function is a linear function. Very good. Fill in the blank. The constant function, oh man. Okay, just gave this away. The constant function, the identity function are 2 special types of linear functions. All right, homework exercises. You've already been assigned either 11 or 13 or both. Any of the odds 15 to 25, either 27 or 29 or both. They have 4 parts each, so you choose. Either 31 or 33 or both. Any of the odds 35 to 39. Do 41. Only one like that, but it has 2 parts. And then do some of the application problems. Odds 43, either 43 or 45. Oh, or 47. Any of the odds 43 to 47. Okay, not a bad idea to look at true false, so you aren't going to see many of these on quizzes and tests. Maybe you'll see something sort of similar, but that would be 49. Think through that, see if you can understand what they're asking. All right. Okay. Let's move on to 1.7. And by the way, let me take a pause here. Okay, because several people have come in since we started. I asked the question early. Looks like I'm going to have quite a pause here. Is anyone here now who did not get a quiz last time? You did, okay? Technically, the quizzes should have been passed out today. But I gave you an extra weekend to work on them if you wanted to. Do you need grant paper? Anyone else need a quiz? All right, good deal. They technically are due 1 week from today now. Okay, so it'll be next Tuesday. If you get them finished sooner, you can turn them in sooner. Okay? If you need more time, it's okay, but please don't fiddle around with it. Because you've got to, and here's something, I hope I said this before, but let me say it again. You've got to turn in the quiz before you can take the test. Okay? Otherwise, you have to ask me politely to give you a 0 on the quiz, and I won't like to do it, but if you ask me, I can't refuse you, can I? So I will have to give you a 0 on the quiz. So please get it in sooner. Why? So you can see what you may have missed. If you wait until the test day to turn in your quiz, it's okay to do it then, but I'd rather you didn't. You don't have any feedback on it. You don't get a chance to see if you missed anything, so you can't correct your errors. So get it in sooner rather than later so you can see what you may have missed. Also, help your classmates out, because I can't return the quizzes until I get them all in. Right now, I don't know who it is, but there's still one person that hasn't picked up a quiz, okay? So that means they still don't even have the quiz yet. So please get them in as soon as you can so I can get them back to everybody. Now, if you turn them in early or just on time or whenever you turn them in, I'll try to have them graded by the next class period. You can come see what you missed, but you can't take it home with you because somebody else still has a quiz out there, and I don't want them happen to land their eyes on the correct answers on your pages and then cheapens your grade. Okay, in other words, you may have missed something, they see what the right answer is, and they get it right, actually make a better grade than you just because they saw your quiz. So I can't return them until I get them all in. So please get them in sooner rather than later. Okay, that was my commercial. Okay, let's go back to the math here. Continuing functions and their graphs. We're now going to talk about transformations of functions. If you remember, the last slide of the last section said rigid or non-rigid transformations. That's what we're going to talk about. We'll use vertical and horizontal shifts to sketch the graphs of function. I've already given you a hint on one vertical shift we had. We'll use reflections also to sketch graphs of functions. And then we'll use non-rigid. These two are rigid transformations. We'll use non-rigid transformations to sketch graphs of functions. Guess what they're focusing on? Sketching graphs of functions. They love sketching graphs, okay? So let's look at some of these shifting graphs, these graft and corruption here, shifty things here. All right, many functions have graphs that are transformations of those parent functions. That's why we looked at and did the parent functions last time and recognized the graphs. For instance, you can obtain this one, h of x is equal to x squared plus 2. What do you reckon is the parent function here? The squaring function, okay? And what you're doing to the squaring function? Adding 2 to it. Now the squaring function, if this was, say, alpha of x equal x squared, what is that? What value is alpha of x? Y. So you're taking the y value of your squaring function, your parent function, that parabola we had, and increasing it by 2. This is the y for the new function. It's up 2. Just don't say yours. Okay. So you just take that origin down here, move it up 2, and then take every point here, 1, 1, and minus 1, 1, move them up 2, and they become minus 1 and 1 becomes 3. And these were at 4, they would go up 2 and be at 6. So every point is elevated 2. By shifting the graph of alpha of x equal x squared, which is the grade function here, up 2 units, okay, as shown here. Now you notice the shape of the function is exactly the same. It does not change. That's why we call this a rigid transformation. It moves it in bulk, keeping the shape just like it is. Does that make sense? All right. So what we did, h of x was the parent function at x squared, which is alpha of x, plus 2. So we took the alpha of x and moved it up, shifted it up 2 units. Every point, point by point, we moved up 2 units. Similarly, okay, different concept here. This time we have a g of x here, which is x minus 2 squared. What do you reckon the parent function is there? X squared again. But this time, what is the difference? You're subtracting 2 from the x, not from the function, right? So guess what kind of shift that's going to be? Where do you find x? On the horizontal axis. So you're shifting horizontally. The vertical, if you're adding or subtracting to the x squared, then you're shifting vertically, okay? So this is shifting. Now here's the difference. Hang on to this. This is as important almost as y is equal to alpha of x equal y, okay? Anytime you're monkeying around with the x value, the x variable, you always do the opposite of what it looks like. A minus 2, what would you think? You would think you go left, you go right, okay? Anything you do with the x is kind of reversed, okay? By shifting the graphs of alpha of x equal x squared to the right 2 units, not to the left. Anything you're doing to the x is generally feels backwards from what you're doing to the y. Okay? Now, here's why that's true. Give me an x. Make up an x. Say it. 3. Okay? If x is equal to 3, 3 minus 2 is 1, and 1 squared is 1. So what would have been here is now over here. What have you done? Gone right 2 units from here to there. Okay? So sure, that's what's happening. Subtract the 2, shift the graph to the right 2, not to the left. Okay? Okay, well, what it's doing is, okay, I don't know if this will help you or not. It helps me because this is, I feel like what's really going on. Okay? Yeah. Okay. Okay. Here's how I look at this. Okay. Goodness, I have to get my pen back. And this is helpful to me. It may not be helpful to you though. Okay. If I were expressing it this way, h of x minus 2 is equal to f of x. Okay. This was my y before. Y minus 2 is equal to f of x. And basically what we're doing before, if you move it to the same side, you're subtracting. And you see this is on the same side. So you're subtracting, but it's still moving to the right. That one was still moving to up, but when you subtract it from it, it's going up. So that and this are more similar. Remember, that was still going up. This is going to the right. Okay. So this is sort of a stretch here, but that's how I think of it. The easier way to think of it, if you're dealing with the x, go the opposite way you would think. Okay. That to me is the easiest way to think of it. I know what's going on here, but it's a little more abstract. But if you just keep that in mind, if you're dealing with the x, if you're dealing with the y value, go in the direction it tells you. We'll see that come up later too. Okay? So in case of this, the functions f and g and f have the following relationship. G of x, which is x minus 2 squared, was your f operating not on x, but on x minus 2. Okay? That's a right shift 2 units. So this list summarizes the discussion about horizontal and vertical shifts. Now, we're always assuming C is positive. Okay? So assume C is a positive real number. The vertical and horizontal shifts of the graph of y is equal to f of x are represented as follows. Vertical shift C units up, take your f of x and add C to it. Move it up 2. Vertical shift C units down, take it down. Okay? 2 units, or C units. Horizontal shift C units to the right, make that an x minus C. Again, everything with x is backwards. Horizontal shift to the left C unit would be f plus C, which would be f minus a minus C. So it is going to the right. So just remember, if you're dealing with the x's, go in the opposite direction, what you would expect, or what you did with the y's. Does that make sense? Maybe not for the y part, but that's how you do it. Okay? Well, that's how I think of it. Just easier to do with that.
Don't say subtract, just say shift.
What's that?
I'm just not going to say subtract.
Okay, right, okay. Now, here's the other thing. What if, okay, so you can do, if that was an x plus 2, then you know going the other way. All right, everybody got it? Okay, that's all people ready. Okay. Some graphs can be obtained from a combination of vertical and horizontal shifts, as illustrated in example 1b. We haven't gotten there yet, but we're going to. Vertical and horizontal shifts generate a family of functions, each with the same shape, but different location on the plane. And that's what we call them rigid transformations. So here's example 1. So use the graph of f of x equal x cubed, that's going to be our parent function, to sketch the graph of each of these functions. Since they told us to use alpha of x equal x cubed, let's graph that first. Okay? There will be my y-axis, there will be my x-axis, or vertical and horizontal if you want to say it that way. Okay? You tell me how to graph this one. Give me some points. Say again? A little louder. Give me an x. 1. Okay, what would be your y then? 1. Okay. Right there, that's that point. Give me another x. 2. What would that y be? Okay, I think that's it. 1, 2, 3, 4, 5, 6, 7, 8 right there. 2, 8 would be up here. Next. 0. 0, I can do that one. Okay. Next. -1, what would that be? -1. Okay, I can do that one. Next. -2, that would be, I don't have room. So it's somewhere way down here. So basically this is what your parent function, the cubic function, looks like. Right? All right, we do that. How would you do G? Let's do G in a different color. You pick a color here. Red. Purple. Okay, purple wins. She said it louder. Okay, so here will be purple. What do you think is going to happen here? Every point down 1. Here it goes down 1. This one goes down 1. This one goes down 1. This one goes, where is it? Right there. It goes down 1. So now this one is like this. Not bad, huh? You didn't have to pick points, evaluate and stuff. You just say every point. You already had them on there. Down 1, down 1, down 1. If we had the minus 8, it would have gone down to -9. Okay, good deal. How about h of x? What color you want it? Now we'll do red. Okay. All right, here's red. Okay. What are you going to do here? Left 2 and up 1. So you go back to your parent function. Left 2, up 1. There would be the first one. Say again?
Oh, so all of that was just for 1.
Yeah, that was for your, the purple one was A. Now we're going to do B. And you pick any point and you go. You see why it's left 2? Left 2, up 1. Next one. Way up here somewhere. Left 2, up 1. Right there. This one down here. Left 2, up 1. It's right here. And then the next one would still be off scale. So it's something like, whoa, I messed that up, didn't I? Something like that. Same shape, supposedly. Okay. Pretty bad shape. Okay. Same shape, every one of those is just located in a different part. That's why they call it a family of curves. Okay? Does that make sense? You see how to do it? Okay, good deal. Any questions about it? And you can plug in values. You could have plugged in a 0 here. And that would have been 0 plus 2 is 2. 2 cubed is 8 plus 1 is 9. Where did you want up? 1, 2, 3, 4, 5, 6, 7, 8. When x is 0, you want up at 9. You can plug in the points and graph them. You get the same result. Just a little bit easier to use those shifts.
But you're going to give us the points, right? Like you're going to actually give us.
You choose your points.
Really?
Yeah, I'm not going to graph the parent function for you.
No, I'm saying like most teachers, they'll give you the points.
Well, it depends on what the question asks.
The points, but the actual.
Oh, I'll give you the functions.
Saying, yeah.
Yeah, I'll give you the function and say, do this to it. Okay?
Yeah.
Okay. Yeah, I'll do that. Just like this
Or
one.
like x would be 6. You're not going to do that.
No, you get to choose which ones you want. I'm not going to take your freedom of expression away from you. You get to choose whatever points you want to graph. So if you had chosen 6 and then cube 6, good luck with that. Okay? All right. Okay. 6 cubed, I think, is what, 216 or something? I'm not going to plot that. You can plot it. I'll let you choose. Okay. So there is our rendition of it. Let's see what they do. Okay, we'll erase all that ink and see what they do. Relative to the graph of f of x equal x cubed, that's their gray graph here. Then they're doing the A part, g of x equal x cubed minus 1. It takes every one of those points and drops them by 1. Okay, they don't show the points as well, but you see that one goes down 1. This one is minus 1, minus 1. That goes down here to minus 1, minus 2. The one up here at plus 1, plus 1. It drops down to plus 1, 0. So every point drops down by 1. Okay? A downward shift of 1 unit. Shown at the right. I was going to say it's not 1 unit to the right. It's shown at the right. Okay, so there's the A one. Here's the B one. Again, we start with the parent function, little gray graph over there. But this time, for every point, and for instance, the first point was 0, 0, we do left 2, up 1. Left 2, up 1. So there's that point. This was a 1, 1, left 2. Right here and up 1, right there it is. This one was a minus 1, minus 1, left 2, up 1, there it is, right there. So every point gets shifted up 1 and left 2. And the order really doesn't matter. I kind of like to do x's first and y's second, but that's just me, okay? And you see it's exactly the same shape, just a transformation. Rigid transformation. Any questions on that? All right. In example 1b, you obtain the same result when the vertical shift precedes the horizontal shift, or when the horizontal shift, that's what I was just saying. Doesn't matter which order you do them, just keep up and do them both. Okay? Now, we're going to reflect on some graphs here, okay, reflecting graphs. Another common type of transformation, which is also, by the way, a rigid transformation, is a reflection. For instance, if you consider the x-axis to be a mirror, then the graph of h of x is equal to minus x squared, okay? Now, what is being negated here? The x squared. The x squared was your y value. And you're negating that with this. So guess what? Any y you had up here now becomes down there. It becomes a negative of that. So that's reflection across the x-axis. Here was your parent function, f of x equal x squared. When you put the negative in front, you're just negating. This becomes a negative 0, if it stays the same. This 1 becomes, both these 1s, at 1, 1 and negative 1, 1 become 1. Negative 1 and negative 1, negative 1. Every one gets shifted, reflected across the x-axis. Okay, yeah. Okay. 1, 1 was on this graph. When you negate it, the 1 stays the same, the x stays the same, the y gets negated. It becomes a 1, negative 1. Over here, you're negative 1, 1, because when you put negative 1 here, you square it, it becomes 1. But now you negate that, and it becomes negative 1, negative 1. Yeah. The next one would have been a 2, 4, but you can't see the 4. It becomes 2, negative 4. That's why it's down here. So everything gets negated because you're negating the function. The function is the y. Okay? You're negating this function here. So it flips it or reflects it across the x-axis. Okay. So they don't show the second part, but we'll do it. They showed this. Reflections in the coordinate axes of a graph of y is equal to f of x are represented as following. Reflection across the x-axis is when you negate the y. It moves it in the other direction. Reflection across the y-axis is when you negate the x, okay? So h of x would be f of minus x. Now, you wouldn't use a squaring function. Why? because that's the same way. What you've done then is taken this one and done like that. It's the same thing. But if it had been a cubic function, then it would have been like this. You negate everything across the y-axis. That one we don't do as frequently. We do negate the function. We can negate the x, but most of the time that's a test for even or oddness, and that's what we use it for. Okay? Any questions on that? Okay? Here's example 2. The graph of this function. Now, they didn't show you this one before, but we talked about it before. It wasn't listed as a parent function, but in fact, it sort of is. Now, remember when you have even exponents, they look like the squaring function. The only difference is, two differences, between -1 and 1, they tend to be flatter near 0 and steeper elsewhere. Okay? The squaring function came down very smoothly with here. The quartic function to the 4th power comes down more sharply here, flatter here, and goes up more sharply there. That's your quartic function. Same thing with x to the 5th to x to the 3rd. Flatter around 0, steeper outside of ±1. So that's going to happen most of the time. So here is a new parent function, you could say. The quartic function, raising something to the 4th power, x to the 4th. Okay? Now, each of these graphs below is a transformation of that first one, the f. Okay? You write the equation of what that would be. What you reckon this one did to what we had before? This first one here, the A one. How did it change that to become this? Okay? You said h to the... What's that? Okay. We're looking at this. That's the parent function that we're dealing with, and we're doing this A function here. What has happened to it? It turned upside down, which would be a negative f of x, and then you add 2 to it. So it'd be minus x to the 4th plus 2. Okay? Good enough. Okay? And actually 2 ways you could express this. I'm going to go back to black, or I can't do black, but I'll do dark blue. You could write this way. Y is equal to negative f of x plus 2, which would be negative x 4th plus 2. That's exactly right. What's that next one doing? Again, with this as your parent function. Okay? Y is equal to f of okay, I agree that you got x minus 3 in here. To the 4th, yeah. Well, no, your f was to the 4th, okay. So that's taking care of that. One thing you're missing, a negative in front. You reflected and then shifted. I like to think of them that way. So this would be y is equal to minus x minus 3 to the 4th. Your f of x minus 3, which would be x minus 3 to the 4th, and then negate that. So the minus sign here, flipped it down, and the minus 3 shifted 3 to the right. Make sense? All right. Y'all are good. You picked up on those really nicely. Any questions on those? Well, let's see how they did them. Let me remove my writing. Everybody got it? Okay. And let's see what they did. Oh, they didn't use that slide anyway. The graph of G is a reflection across the x-axis followed by an upward shift of 2 units to f of x equal x to the 4th. So that would be a minus x to the 4th plus 2. Okay? On the B part, the graph of H was a horizontal shift, and they say followed by a reflection. I still like to do the reflection first, then do the shift. It really doesn't matter, but since you did the reflection first on the other, then, I mean, when I see rules of order of operation, of course, I'm going to negate that before I add it here. And the same thing here. I basically am, they're saying you're shifting first and then negating, which is okay, but I like to negate first and then do the shift. Is the negative sign, yeah. So yeah, I agree with you there too. So that's, what's that? Right. Okay. And he said it made more sense. There's the minus sign, so negate that. Yeah, and then do your shift. Right. Yeah, to the right, because anything dealing with X goes in the opposite direction. Very good. All right, that was example 2. There is a checkpoint there. I suggest you do the checkpoints. All right, let's see. Trying to see where this is. What's that? Yeah, the test will be all, everything we covered in chapter 1, which is 1.4 to 1.9. Yeah. I think that, yeah. The quiz just covered 1.4 to 1.6, and the test will cover 1.4 to 1.9. So basically, the quiz was 1 page. Your test is going to be 2 pages. And this won't be exactly true, but the first page is going to be a lot like your quiz. Definitely not the same questions, and probably leaving out some, adding a few or something like that, but over the same material. And then the second page is going to be the new material from 1.7 to 1.9. So, okay. Though there may be, the bottom of the first page may have a 1.7 question. I mean, I'm not saying it's exactly the same, but that's a general rule. Okay. Oh yeah, there I see it. Okay. This verbiage is at the bottom of page 70 before they do example 3. And they don't do example 3, so it's a summary of what we did with example 3, and we're barely going to be able to get started. But let's get started on example 3. Let's do it on this page because we have a lot of white. Let's see if, oh, we have more white here. So let's do example 3 here, or at least get started. Compare the graph of each function with the graph f of x equals square root of x. F of x equals square root of x. That's our parent function. So you tell me how to graph that. 0, 0 is certainly going to be there. Okay, it's going to start increasing. What's another point? 1 what? 1, 1. Okay, you're stuttering, or that's it. Okay, got it. Next. I like that. I'm not going to mess around with those. I don't know what it is, but I do know it's the square root of 4 is going to be 2. So that's going to be right here. Next one. 9, 3. It's going to be something about like that. And if we had room, I don't think we do, 10, 11, 12, 13, no, we don't. But anyway, that's what your square root function looks like. Right? Or thereabout. I may not be going up quite fast enough or something, but, you know. Yeah, get out of there. Okay, something like that. Okay. Yeah, we're not going to have time to do any more. Remember that for next time. We'll begin next time with right there. All right. Let me give you a few homework exercises in this group, okay? This section. We came close to racking up here. Okay, do any of the odds are either 5 or 7 or both? I'll let you just decide. Then I would do 9. Then I would do 11 or 13. Then I'd do any of the odds 15 to 19. and then try to do any of the odds 21 to 45. Actually, you can stop at 41 if you'd like, because we haven't done the square root functions. We'll do those. So 21 to 41. We'll pick up the rest of them next time. Good deal. Any questions? All right, you got your quizzes. Hope you're working on your quizzes. And by the way, this class has been fairly good. I've already got 3 papers in out of 20 people, but hopefully more will be coming soon. Don't let those get too far behind. If you're ready for the quiz, I'll take it. Good deal. Okay. Good deal. We will see you on Thursday. All right. What's that? No, okay. Basically, what you do, you graph it first, and then you figure out where it's increasing and decreasing.
So, like, I had to just write the order pairs there?
Well, whatever the graph takes. Like, okay, if this was your function, if it was doing this here and doing this down here, something like that, then let's say the other part of the function was like this. It would have been decreasing from here to there, increasing there, and increasing there. So, or something like that. So you draw the graph, see how it looks, and get your discontinuity in there, because it's piecewise defined. And then on the whole graph, where is it increasing, where is it decreasing? If this was a squaring function over here, like this, well, this would be increasing everywhere from here on, but it's not even defined here. It stops right there, so then you go here. Yeah. Does that make sense? Is that what you did? Okay. That looks to me like number 1. Okay. Oh, which are you doing? This is 10. 10 is this one down here. Okay. 9 is that one? No. Where's 9? I don't see 9. Okay, yeah, okay. But yeah. Good. What's that? Yeah, right. Well, it doesn't have a graph in the back, but you could have done that. Yeah. So I don't know. Since I can't see your work, I can't judge it. But no, yeah, I think you got the general idea. Okay. Good deal. Good for getting it in early too.